From the moment humans first gazed upon the starlit sky, a profound question has echoed through the ages. Why is there something rather than nothing? This question extends beyond our everyday experiences, touching upon the very fabric of reality and the fundamental laws governing the cosmos. Today, as we stand at the precipice of unprecedented scientific discovery, this age-old question remains as relevant and mysterious as ever. We find ourselves equipped with powerful telescopes that peer deep into the cosmic expanse, revealing a universe more vast and awe-inspiring than our ancestors could have ever imagined. Despite remarkable advances, the fundamental question of why our universe exists with its particular set of laws continues to elude a definitive answer. Our quest is not merely to understand the physical processes that govern the universe, but to grasp the underlying principles that breathe fire into the equations, transforming them from mere mathematical abstractions into the tangible reality we experience. At the heart of our exploration lies a profound realization: the universe in all its complexity and grandeur appears to be governed by a remarkably small set of fundamental laws. These laws, often expressed in the elegant language of mathematics, provide a framework for understanding the intricate workings of everything from the smallest subatomic particles to the largest cosmic structures. But this remarkable ability of mathematics to describe the natural world raises a new set of questions. If the universe is indeed governed by these mathematical laws, where did these laws originate? Are they fundamental, immutable aspects of reality, or could they be emergent properties arising from a deeper, yet unknown level of existence? These questions lead us to the very edge of our current scientific understanding, into a realm where physics, philosophy, and metaphysics intersect. Our goal is not to simply present these theories as fantastical possibilities, but to explore their scientific underpinnings, their strengths, their weaknesses, and their potential to shed light on the fundamental question of why our universe exists as it does. Throughout history, the search for the origin of the universe and its laws has been a driving force behind human curiosity and ingenuity. Ancient civilizations wove intricate myths and cosmologies, attributing the creation of the world to powerful deities and primordial forces. The development of modern science, with its emphasis on observation, experimentation, and mathematical rigor, marked a turning point in our quest to comprehend the cosmos. From Copernicus's heliocentric model to Einstein's theory of general relativity, each scientific breakthrough has brought us closer to unraveling the mysteries of the universe's origins. Today, we stand on the shoulders of these scientific giants, armed with an arsenal of sophisticated tools and theoretical frameworks. Yet despite these remarkable advances, the ultimate question of what sparked the Big Bang itself, and what, if anything, came before, remains shrouded in mystery. One of the most intriguing aspects of our exploration is the sheer diversity of theories that have been proposed to explain the origin of the universe's laws. From the mind-bending landscapes of the multiverse to the elegant symmetries of Noether's theorem, the possibilities are as vast and varied as the universe itself. Some of these theories challenge our very understanding of what it means for something to be fundamental. Could it be that the laws we perceive as immutable and eternal are, in fact, emergent properties arising from a deeper level of reality? As we navigate this landscape of theories, it's important to remember that we are not searching for one definitive answer, but rather seeking to develop a deeper understanding of the range of possibilities and the evidence that supports or challenges each. Despite the diversity of theories and the inherent challenges in probing the universe's origins, there's a glimmer of hope in our quest for understanding. Many physicists and cosmologists believe that a deeper, more fundamental principle underpins the seemingly disparate laws of nature. This principle, if discovered, could provide a unifying framework for understanding not only the origin of our universe, but also the potential for other universes with their own unique sets of laws. This search for a unifying principle has driven some of the most groundbreaking scientific discoveries in history. Today, the search for a theory of everything that can unify gravity with the other fundamental forces remains one of the most ambitious and challenging goals in modern physics. Our exploration will take us on a journey through this fascinating landscape of theoretical physics, examining the strengths and weaknesses of various approaches, from string theory to the intriguing possibility that information itself might be a fundamental constituent of reality. As we embark on this cosmic quest, it's crucial to establish a framework for understanding the vast and often mind-boggling concepts we'll encounter. Our journey will take us through a landscape of diverse and sometimes competing theories, each offering a unique perspective on the universe's origins and the nature of its laws. We'll begin our exploration with the mind-bending concept of the multiverse, the idea that our universe may be but one among an infinite number of universes, each with its own set of physical laws and constants. This notion, once relegated to the realm of science fiction, has gained traction in recent years, fueled by advances in fields such as string theory and inflationary cosmology. We'll delve into the evidence supporting the multiverse hypothesis and explore its implications for our understanding of fine-tuning and the Anthropic principle. Next, we'll journey back to the universe's earliest moments, exploring the enigmatic epoch of cosmic inflation. We'll examine how quantum fluctuations during inflation could have given rise to the seeds of galaxies, and how this process might hold clues to the emergence of physical laws. Our exploration will extend beyond the familiar realm of particles and forces, venturing into the realm of emergent phenomena and self-organization. We'll encounter the idea that the universe's laws might arise from simpler, underlying principles through processes of self-organization and emergence. Just as complex patterns can emerge from the collective behavior of simple agents, could it be that the intricate laws of physics we observe are themselves emergent properties of a deeper, more fundamental reality? We'll delve into the fascinating world of complexity science, exploring how order and structure can spontaneously arise from seemingly chaotic systems. Our journey through the landscape of theoretical physics will also lead us to explore the profound connection between conservation laws and symmetries in nature. Noether's theorem reveals a deep link between these two concepts, demonstrating that every conservation law is associated with a corresponding symmetry in the laws of physics. As we push the boundaries of our understanding, we'll encounter the intriguing possibility that information itself might play a more fundamental role in the fabric of reality than previously thought. Throughout our exploration, we'll encounter the intricate interplay of entanglement with the very fabric of spacetime itself. Entanglement, which Einstein dubbed spooky action at a distance, describes the correlation of quantum particles over vast distances. Recent research suggests entanglement might play a crucial role in the emergence of spacetime itself. We'll delve into how quantum entanglement challenges our classical intuitions about locality and causality. This phenomenon might hold the key to understanding the emergence of spacetime, revolutionizing our understanding of the universe. Our journey into the cosmos begins with a leap beyond our observable universe. Imagine a reality so vast that our universe is but a single bubble in a cosmic sea. This is the multiverse, an infinite tapestry of possibilities. Once myth, now a legitimate theoretical possibility. Advances in cosmology and quantum mechanics fuel this idea. The multiverse offers a glimpse into a grander reality. The multiverse is a complex concept with various theoretical underpinnings. Different models offer unique perspectives on parallel universes. Cosmic inflation suggests exponential expansion after the Big Bang. This theory from the 1980s explains the universe's rapid expansion. Inflation smoothed out the universe, creating the vast cosmos we see today. Some physicists believe inflation is an eternal process. This creates a cosmic bubble bath of universes. Each bubble could evolve into a separate universe with unique laws. String theory offers another pathway to the multiverse. It posits the universe is made of tiny, vibrating strings of energy. These strings vibrate in different ways to create particles and forces. The strange and counterintuitive world of quantum mechanics also offers a potential window into the multiverse. One of the most mind-boggling aspects of quantum mechanics is the concept of superposition, which states that a quantum particle can exist in multiple states simultaneously until it is observed. This seemingly paradoxical idea has been experimentally verified countless times, demonstrating the probabilistic nature of the quantum world. One interpretation of quantum mechanics, known as the many worlds interpretation, takes this idea of superposition to its logical extreme. According to this interpretation, every time a quantum measurement is made, the universe splits into multiple parallel universes, each representing a different possible outcome of the measurement. In this view, there's a universe where the cat in Schrödinger's famous thought experiment is alive, and another where it's dead. And in each of these universes there's a copy of you observing the corresponding outcome. While the many worlds interpretation remains a controversial interpretation of quantum mechanics, it has gained increasing support among some physicists in recent years. If true, it would imply that the multiverse is not merely a theoretical possibility but rather an inevitable consequence of the fundamental laws of quantum mechanics. These are just a few of the theoretical pathways that lead to the concept of the multiverse. The multiverse hypothesis, while intriguing, raises a fundamental question: if these other universes exist, can we ever hope to detect them? After all, if these parallel realities are truly separate and causally disconnected from our own, how could we ever hope to observe them, let alone interact with them? While direct observation of other universes might be impossible, some physicists believe that we might be able to detect their subtle influence on our own universe. One possibility is that collisions between our universe and other universes in the distant past could have left behind observable imprints on the cosmic microwave background radiation, the faint afterglow of the Big Bang. These collisions, if they occurred, could have created subtle temperature variations or patterns in the cosmic microwave background that would be difficult to explain by standard cosmological models. Scientists are actively searching for these telltale signs in the data collected by telescopes like Planck, hoping to find evidence of these cosmic encounters. Another avenue of exploration lies in the realm of high-energy physics. Some physicists believe that the Large Hadron Collider, the world's most powerful particle accelerator, might be able to create microscopic black holes that could offer a glimpse into extra dimensions, which are predicted by some models of the multiverse. While the possibility of creating these mini black holes remains uncertain, the LHC continues to push the boundaries of our understanding of the universe at its most fundamental level. The concept of the multiverse, beyond its scientific implications, raises profound philosophical and even existential questions. If our universe is just one of countless others, does it diminish our own significance in the grand scheme of things? Does it render our search for meaning and purpose futile? On the contrary, the multiverse hypothesis, if true, could be seen as expanding rather than diminishing the richness of existence. It suggests that the universe is far more vast, more diverse, and more full of potential than we ever imagined. It challenges us to confront the limits of our own perception and to embrace the awe-inspiring mystery of the cosmos. The multiverse, far from rendering our existence meaningless, could be seen as a testament to the boundless creativity of nature. It suggests that the universe is not a static, unchanging entity, but rather a dynamic, ever-evolving tapestry of possibilities. And within this vast cosmic canvas, our own universe, with its unique laws and its capacity for life, consciousness, and wonder, holds a special place. The search for understanding, for meaning, for our place in the grand scheme of things, is a journey that has captivated humanity since the dawn of consciousness. The multiverse hypothesis, while still in its infancy, offers a new and exciting chapter in this ongoing quest, inviting us to expand our horizons, to challenge our assumptions, and to embrace the boundless possibilities that lie hidden within the fabric of reality. Our journey begins in the early universe, a realm of unimaginable heat and energy. Here we encounter cosmic inflation, a theory revolutionizing our understanding of the Big Bang. This theory explains the universe's structure and the emergence of galaxies. Imagine a universe undergoing rapid exponential growth, a tiny speck of spacetime inflating faster than light. This explosive expansion smoothed spacetime, creating the vast universe we see today. To understand how inflation solves these cosmological conundrums, imagine a balloon with small dots scattered across its surface. As you inflate the balloon, the dots move farther apart, and the surface of the balloon stretches and becomes smoother. Cosmic inflation, in a similar way, stretches the fabric of spacetime, smoothing out any initial irregularities in the distribution of energy and matter. Before inflation, the universe was a chaotic and turbulent place with regions of vastly different temperatures and densities. These variations, if left unchecked, would have led to a universe far more clumpy and inhomogeneous than the one we observe today. Inflation, by stretching the universe exponentially, essentially dilutes these initial variations, spreading them out over vast distances. The flatness problem is similarly addressed by inflation. Imagine a tiny ant crawling on the surface of a balloon. To the ant, the surface appears flat, even though we know the balloon is curved. Inflation, by dramatically increasing the size of the universe in a short amount of time, effectively flattens out the curvature of space-time from our perspective, just as inflating the balloon makes its surface appear flatter to the ant. In essence, inflation acts like a cosmic reset button, erasing the universe's initial conditions and setting the stage for the smooth, homogeneous cosmos we observe today. It's like taking a crumpled piece of paper, smoothing it out, and stretching it taut, creating a blank canvas upon which the grand cosmic drama of star formation, galaxy evolution, and ultimately life itself could unfold. Inflation's smoothing effect explains the universe's large-scale homogeneity and introduces the seeds of cosmic structure. Galaxies and clusters originated from quantum fluctuations during inflation. Quantum mechanics intersects with the cosmic stage, connecting the smallest and largest scales. In the quantum realm, emptiness is a seething cauldron of virtual particles. These particles, amplified by inflation, became density variations. These variations, amplified by gravity, formed galaxies and clusters. The cosmic microwave background radiation provides evidence for this quantum origin. Tiny temperature fluctuations are imprints of primordial quantum fluctuations. It's as if we're looking back in time, witnessing quantum whispers etched onto the cosmos. The universe's evolution is a story of order arising from chaos. Initially smooth, quantum fluctuations played a significant role. In chaos, these fluctuations would be lost, but in a smooth universe they were amplified. This balance sowed the seeds of complexity, crucial for the structures we observe today. Without inflation, the universe would lack galaxies and stars. Our existence to ponder this is profound. Inflation connects quantum mechanics to cosmic structure. Tiny fluctuations shape the destiny of stars, galaxies, and life. As we delve deeper into the mysteries of cosmic inflation, we encounter a tantalizing question. Could this period of rapid expansion hold clues to the origin of physical laws themselves? The idea that the laws of physics, often considered fundamental and unchanging, might have emerged or evolved during the universe's earliest moments is a radical one, but it's a possibility that some physicists are beginning to explore. One intriguing possibility is that different regions of the inflating universe could have settled into different vacuum states, each characterized by a unique set of physical laws and constants. In this scenario, our universe, with its particular set of laws, would be just one pocket in a much larger multiverse where other regions might have drastically different physics. This idea of cosmic inflation leading to a multiverse is still highly speculative, but it offers a potential explanation for why our universe appears so fine-tuned for life. If an infinite number of universes exist, each with different laws and constants, it's not surprising that we find ourselves in one that's hospitable to our existence. While the connection between inflation and the origin of physical laws remains an open question, it highlights the profound implications of this brief but crucial period in the universe's history. Cosmic inflation, it seems, was not merely a period of rapid expansion, but a time of immense creative potential. A time when the fundamental properties of the universe, from its structure to its very laws, may have been forged in the crucible of the early cosmos. Our exploration of the universe's origins has led us through the multiverse and the explosive birth of our cosmos. Quantum fluctuations sowed the seeds for galaxies and stars. The fine-tuning of the cosmos for life is a profound mystery. Fundamental constants appear exquisitely balanced. These constants determine the properties of atoms, molecules, and stars. The universe is balanced on a razor's edge. The Goldilocks Enigma. The universe's fine-tuning extends to fundamental forces and particle masses. The proton's mass is crucial for atomic stability and chemistry. The cosmological constant's precise value allows galaxy formation. The Anthropic principle suggests the universe must support observers. We exist because the universe supports life. The strong Anthropic principle suggests the universe is compelled to give rise to observers. It raises questions about a cosmic designer or unknown physical mechanisms. The debate highlights the limits of our scientific understanding. Some questions might lie beyond empirical science and metaphysics and belief. A universe made for us? The fine-tuning of the universe raises profound questions about our place in the cosmos. Are we special, or is it just a cosmic lottery? If the multiverse exists, our universe's fine-tuning is a statistical inevitability. We observe a life-friendly universe because we can. The multiverse doesn't eliminate the philosophical implications of fine-tuning. What determines the laws of physics in different universes? Could there be a deeper level of reality, a meta-universe? The fine-tuning of the universe, whether explained by the Anthropic principle or some other yet unknown mechanism, highlights a profound shift in our understanding of our place in the cosmos. For centuries, humanity viewed itself as occupying a privileged position at the center of the universe, only to be humbled by the realization that our planet is but a speck of dust orbiting a typical star in a vast and ancient galaxy. Now, the fine-tuning enigma, coupled with the mind-boggling concept of the multiverse, suggests that even our universe, vast as it is, might be just one of countless others, a single note in an infinite cosmic symphony. Yet within this humbling realization lies a glimmer of hope, a suggestion that our existence, however small and insignificant it might seem on a cosmic scale, might be deeply intertwined with the very fabric of reality. The Anthropic principle, in its strongest form, hints at the possibility that our emergence as observers was not merely a fortunate accident, but rather an integral part of a grand cosmic design. It suggests that the universe, in some sense, wanted to create observers, that our existence as conscious beings capable of appreciating its beauty and complexity was somehow written into its very fabric from the beginning. Whether or not this interpretation of fine-tuning proves to be correct, it serves as a powerful reminder of the profound mystery and wonder of the universe we inhabit. Our exploration of the universe's origins has taken us through the multiverse and the explosive birth of our cosmos. Now we turn to emergent laws and self-organization. Imagine a bustling city, a complex web of human activity. Its complexity emerges from the bottom up. This concept of emergence is seen everywhere in nature, from snowflakes to the human brain. Could the laws of physics be emergent properties? This is the tantalizing possibility we'll explore. To grasp the essence of emergence, it's helpful to consider some familiar examples from the natural world. Take, for instance, the intricate beauty of a snowflake. Each snowflake is unique, a testament to the countless ways in which water molecules can arrange themselves as they freeze. Yet this intricate complexity arises from a remarkably simple set of rules, the basic properties of water molecules and their interactions with each other. As water molecules cool and lose energy, they begin to slow down and form weak bonds with their neighbors, arranging themselves into a crystalline lattice. The specific shape of the snowflake is determined by the precise arrangement of these molecules, which in turn is influenced by factors like temperature, humidity, and even the presence of tiny dust particles that can act as nucleation sites for ice crystal formation. Another striking example of emergence can be found in the flocking behavior of birds. A flock of starlings, for instance, can move with remarkable coordination, swirling and diving as if guided by a single mind. Yet there's no leader dictating the flock's movements. Instead, each bird follows a simple set of rules, such as staying close to its neighbors while avoiding collisions. The complex, mesmerizing patterns of the flock emerge from the interplay of these simple, local interactions. It's a testament to the power of self-organization, where order and complexity arise spontaneously from the bottom up, without the need for a central controller or a predetermined plan. The concept of emergence, while well established in fields like biology and complex systems, might seem like a radical departure from the traditional view of physics, where the laws of nature are often regarded as fundamental, unchanging, and independent of the systems they govern. However, some physicists believe that the universe itself might be the ultimate example of a self-organizing system, its very laws emerging from a deeper level of reality. One of the most intriguing areas where this idea is being explored is in the realm of quantum gravity, the theoretical framework that seeks to unify quantum mechanics and general relativity, the two pillars of modern physics. Quantum gravity aims to describe the behavior of spacetime at the smallest scales, where the quantum nature of gravity is expected to become significant. One of the leading contenders in quantum gravity is loop quantum gravity, which proposes that spacetime itself is not a smooth, continuous fabric, as envisioned by general relativity, but rather a network of interconnected loops, much like a chainmail suit. These loops, at the Planck scale, the smallest possible unit of spacetime, are thought to interact and evolve according to a set of quantum rules. What's particularly intriguing about loop quantum gravity is the possibility that the familiar laws of physics, including gravity itself, might emerge from the collective behavior of these underlying loops. Just as the smooth flow of water emerges from the chaotic motion of countless molecules, the smooth curvature of spacetime, as described by general relativity, might arise from the intricate interactions of these quantum loops. The concept of emergence, while well established in fields like biology and complex systems, might seem like a radical departure from the traditional view of physics, where the laws of nature are often regarded as fundamental, unchanging, and independent of the systems they govern. However, some physicists believe that the universe itself might be the ultimate example of a self-organizing system, its very laws emerging from a deeper level of reality. The idea that the laws of physics themselves might be emergent has profound implications for our understanding of the universe and our place within it. If the laws of nature are not fixed and immutable, but rather arise from a deeper level of reality, it suggests that the universe is far more dynamic and malleable than we previously thought. Imagine a universe where the laws of physics are not etched in stone, but rather encoded in the very fabric of reality, much like software running on a computer. In this scenario, the universe's evolution would be akin to a cosmic program, its laws and constants evolving over time, perhaps even adapting to changing conditions. This notion of a cosmic code challenges our traditional understanding of the relationship between mathematics and the physical world. Instead of mathematics being merely a tool for describing reality, it suggests that mathematics might be the very language in which reality itself is written. The universe, in this view, would not just be described by mathematics, it would be mathematics. This idea, while still highly speculative, has profound philosophical implications, blurring the line between the abstract realm of mathematics and the concrete reality we experience. It suggests that the universe might be far stranger and more wondrous than we ever imagined, a place where the very laws of nature themselves are subject to change and evolution. The concept of emergent laws and self-organization offers a tantalizing glimpse into a universe where complexity arises not from top-down design, but from the bottom-up interactions of countless constituent parts. It suggests that the universe is not a static, unchanging entity, but rather a dynamic, ever-evolving system, constantly exploring new possibilities and creating new levels of order and complexity. While the idea of emergent laws is still in its infancy, it has the potential to revolutionize our understanding of the universe and our place within it. It challenges us to look beyond the surface of things, to seek out the hidden connections and underlying principles that govern the behavior of the cosmos. The quest to understand the origin of the universe's laws is ultimately a search for meaning and understanding in a vast and often overwhelming cosmos. It's a journey that takes us to the very limits of human knowledge, forcing us to confront the profound mysteries that lie at the heart of existence. Whether or not the laws of physics ultimately prove to be emergent, the exploration of this possibility has already enriched our understanding of the universe and our place within it. It reminds us that the universe is far more complex, more subtle, and more wondrous than we could have ever imagined, a place where the search for knowledge is an endless and endlessly rewarding endeavor. As we draw our cosmic exploration to a close, we find ourselves standing at the intersection of awe and uncertainty, filled with a sense of both profound wonder and the humbling realization of how much remains unknown. We've journeyed through the multiverse, witnessed the Big Bang, and explored emergent laws. What breathes fire into the equations? What transforms mathematics into reality? The quest to understand the universe's laws is a journey without end, with the McGinty equation, the unified equation of physics, as our guide. Gap 7s. Let's break down a complex physics concept like the McGinty equation, MEQ, into something a bit more manageable. Imagine we're trying to understand how Schrödinger's cat, thrown into a series of increasingly bizarre scenarios, might land. This isn't just any cat, it's a metaphor for subatomic particles that will help us grasp the concept of wave functions in fractal energy fields. First, we start with the basic idea of a wave function, psi QFT xt, which in the world of quantum physics, helps us predict where these tiny particles are and how they're moving. Kind of like guessing where Schrödinger's cat might land after being thrown off the couch. Simple enough, right? Next, we introduce a new twist with psi fractal xt. This is where things get really interesting. Imagine if the room Schrödinger's cat is being tossed into suddenly morphs into a fractal pattern, changing the game entirely. This new term considers how the fractal nature of the environment, a repeating pattern that gets infinitely complex the closer you look, affects the cat's landing. We then combine these ideas to form a new, unified equation. This equation is our attempt to predict Schrödinger's cat's landing, factoring in the crazy fractal environment. It's like trying to calculate exactly where the cat will land on its feet if the room suddenly turns into a swirling pattern tornado. But we're not done yet. Just as the story evolves, so does our equation, with new terms for energy levels and decay rates introduced to account for how this fractal environment influences the cat's energy, and how quickly it can adapt or change its state. Imagine Schrödinger's cat wearing a jetpack, representing energy levels, or a parachute, decay rates, to help it navigate the fractal landscape. Finally, our grand equation is like the ultimate guide to predicting Schrödinger's cat's journey through this fractal world, incorporating everything from how fast the cat was thrown off the couch to how the fractal patterns affect its flight and landing. Who knew throwing a cat off of the couch could teach us new things about quantum mechanics? While our exploration has shed light on some of the universe's most profound mysteries, it has also raised new questions, pushing the boundaries of our knowledge. We still don't have definitive answers to questions like, what caused the Big Bang? What is the nature of dark matter and dark energy? Are there other universes beyond our own? These unanswered questions are a call to action, an invitation to continue the quest for knowledge. The universe demands humility, curiosity, and determination. It's a journey that belongs to all of us, a shared exploration of the grandest mystery of all, the universe itself. Our exploration of the universe's origins has only just begun. There are countless mysteries yet to be unraveled, countless questions yet to be asked. The quest for knowledge is a never-ending journey, and the universe is full of surprises waiting to be discovered. We invite you to continue this journey with us. Explore the resources and links provided below to delve deeper into the topics we've covered, from the multiverse hypothesis to the concept of emergent laws. Share your thoughts and questions in the comments section below, and join the ongoing conversation about the universe's origins and our place within it. The universe is a vast and mysterious place, but it's also a place of incredible beauty, complexity, and wonder. By embracing curiosity, fostering collaboration, and never losing sight of the big questions, we can continue to unravel the universe's secrets and deepen our understanding of this extraordinary cosmos we call home. Thank you for joining us on this cosmic adventure. Stay tuned for our next exploration, where we'll delve deeper into the mysteries of fine-tuning and the anthropic principle, examining the philosophical and scientific implications of a universe seemingly designed for life.